So let's do an example problem where let's imagine that we have a rotating disk. So we have a disk, the disk, okay, the disk has a mass of 1.66 kilograms. It has a radius of 11.4 centimeters. And initially, let's say that the disk is rotating at 125 radians per second. So it's going pretty fast. And I want to stop it. And the way I'm going to stop the disk is I've got a little plunger I'm going to push into the side of the disk. As it's going by, friction is going to act as a torque to slow the disk. And so I want to know how hard do I have to push the disk into the, how hard do I have to push the plunger into the rotating disk to stop it? So we need to know the coefficient of friction between the two. And we're going to say the coefficient of friction is 0.215. Okay, and I don't just want to stop it, I want to stop this in only 3.22 seconds. Okay, so I want to know, as I said, what force do I have to use to push that plunger into the disk? Okay, so think about what's happening here. Okay, so this is being pushed in right here with some force. Okay, this is rotating like that. Now, there's a coefficient of friction in here, so if it's trying to move this way, the frictional force is going to be that way. That frictional force is at some radius r, so there's a torque. The torque is going to be r times the frictional force. Okay. So, the frictional force is going to be mu times the normal. So this is going to be equal to r times mu sub k times the normal. Okay, so how does that help me any? Well, I know that torque equals I alpha. So if I could find, so I know that the torque, okay, is going to be mu sub k, times the r times the normal, and that's going to be I alpha. Okay, so I know this, I'm given that, I'm trying to find the normal, so if I could figure out those two, I'd have it made, because then I could solve. So the normal would be I alpha divided by mu sub k times r. Okay, so all I have to do is find I and alpha. Well, actually, that's not hard, because I said this was a disk, and if you look in the book, then the moment of inertia of a disk is 1/2 mr squared. We know what 1/2 is, we know what m is, we know what r is. So that means that I is going to be 1/2 times the 1.66 kilograms times 0.114 meters squared. So I is going to be equal to 0.0946 kilogram meter squared. So we got I. So all we have to do is find alpha. Well, we know that omega equals omega naught plus alpha t. Okay, so alpha is, we know that the final, we know that the final omega is 0. So that means this is minus omega naught over t. Well, we know the omega naught was 125 radians per second. T was 3.22 seconds, so alpha is going to be minus 38.8 radian per second squared. Okay. Now, we've got the torque. Now, really, the torque is going to be minus I alpha rather than I alpha because it's slowing down. And so that means that we now have everything. So really, there should have been a minus in here, minus I alpha divided by mu sub SR. So we have all those terms. So if we plug in all the numbers here, this is going to be I, which was 0.0946 kilogram meter squared times alpha, which was 38.8 radian per second squared. And then we divide by mu sub s, 0.215, and we divide by r, which is 0.114 meters. And so the answer comes out to be 150. Now let's check. Radian is like a placeholder in here. It's not really a unit. So we got kilogram meter squared per second squared divided by meter. It's a kilogram meter per second squared. That is a newton. So the answer is 150 newtons.